So my name is Jared Robbins. I'm giving my 6-minute talk on CPU heat sinks. So first, I'll go over a couple objectives. And give you a basic concept behind CPUs, how they work, why they produce a good amount of heat, what is a heat sink, and kind of how they're designed. The heat transfer equations that are, it's the simple ones, but it's used to derive some of the equations I'll show you at the end of this, and then the heat sink design and the important considerations when designing. So starting off with the simple CPU concept, it's the most critical component in your computer. It's basically the brain to a human, that's kind of what you can translate it to. It executes commands through things called transistors. It's basically yes or no, do this or don't do this. And it's all relayed, like I said, through transistors, which are small electrical circuits. So the more information you're processing at a time, the more heat, the more electricity you're sending through these microscopic transistors, which are seen here from this photo I found online. And the more of that you have, the more heat that you're going to generate. So usually CPUs, I mean, around full load, you can get up to temperatures around 170, 200 degrees Fahrenheit, somewhere around there. So that's where you need a heat sink so that the material that your CPU is made of, or these small microscopic transistors are made of, doesn't just melt. So heat sinks. To prevent that damage, you want to create a heat sink that is basically finned, as you can see here. It's these surfaces that extend from the element, and the quantity of heat transfer depends on the three forms of heat transfer, which are conduction, convection, and radiation. It's mostly conduction and convection. I haven't learned a whole lot about radiation, some basic equations, but yeah, mostly conduction and convection. So these are the governing heat transfer equations. Pretty simple. K and H are heat transfer coefficients, one for conduction and one for convection. And then you've got some temperature gradients and the area. So when designing heat sinks, it's kind of, you can't really change your CPU is going to produce a temperature, and your outside temperature is more than likely air. So you can't really adjust those values of temperature to create more heat transfer. So you have to look at changing the area or the surface area, as she mentioned. So going into a heatsink design, these are two common heatsink or fins, I guess, with two common fin designs. And you're looking to maximize your efficiency when designing these. So these are the equations that would be used to calculate the efficiency for those. And that LC is a characteristic length, so that's kind of the determining factor. You know, if you create a really long fin, you might have too much material and you're not going to be very efficient. So going into the important considerations, like I said, you don't want to use excess material, especially in laptops. You want to consider how much real estate you have inside. So you want to be as efficient as possible, but use up as little space as possible. Your material selection, you want a high conductivity, and it's often material often used is copper or aluminum, and so usually you want to design these around the worst case scenario. So that's when your CPU's at full load and you're producing the most heat. So there's some really long equations, but this is some really long equations to produce or to calculate the overall amount of heat transfer. And then, as it says down there, this theta B equals your chip temperature of your CPU minus your air temperature. So knowing your overall heat transfer, you can work backwards and get your chip temperature based on your fin design, based on this area of the fin and the area of the total fin array. So doing that, you can see what your chip temperature will be, and if it's obviously if it's above the rated temperature for the material that your CPU is made out of, then you're not looking good. So That's kind of how you can work back. It's kind of iterative process where you're seeing how much it'll dissipate, how much heat it'll dissipate, and then calculating an efficiency, and then going back and seeing if that's okay. So once you have that, you can calculate an overall fin array efficiency. So going back and forth with seeing how the design of your singular fin works, and then putting it into an array, calculating your overall heat transfer or heat dissipation, and throwing it into this equation, and you'll see how efficient your fin array actually is. That's it. Questions?
Yeah, so question for you. Okay. Yes,
We got one back there.
okay, yeah, okay. So
Do you know what material, like, the inside of a CPU is made out of so that it doesn't melt under those high temperatures?
Silicon,
Is it?
pretty sure.
Yeah, the chip itself is like a silicon.
Yeah.
Or like
The resistors are
the
usually,
metal like framework, is it metal in there?
I mean, the resistors would probably be, I don't know, some copper.
Maybe copper.
Yeah, copper, but the chip itself is made of silicon. That's why there's a bunch of shortages.
silicon.
Silicon?
I think some other chips actually uses germanium too. Not common. Like either silicon or germanium. You can check it out too. Though I'm sure silicon is kind of the most common, but I guess some few things is germanium. So this is my question for you. Yeah, you talked about CPU. Very interesting. Talk about the heat sink, and then you did not talk about the fan.
Well, I mean,
The fan, like the cooling fan.
yeah, the fan is
So
just
what do
blowing.
they do? Like why fan? Why?
It's like the fluid through a shell and tube. Like a pump pumps fluid through a shell and tube heat exchanger. The fan's going to pump fluid over the heat sink so that you can.
Let me see if you have any equations.
No, I don't.
Go slowly.
No, I don't.
Move forward, yeah. Move forward, like keep going forward. Okay, stop there. Okay, conduction, convection, and radiation. So once you put a fan, right? What happens? Which of the mode of heat transfer will increase?
Convection.
Okay, looking at those, which of the properties will change?
It's your temperature gradient is going to change. It's in that convection equation, as you pump new
As
air
you
over
allow
it,
air to move
you're gonna have
faster,
a-
like what changes? Is there look at the equation?
the
Like,
T infinity. T infinity.
no, not heat infinity. It's actually your H that changes. Your overall heat transfer coefficient, H. The
I thought that was just a property of the air.
Yeah, it's a property of the, and it also depends on the velocity of the air. It's
Okay.
not fixed. It's not constant.
I think
Universal number,
Yeah, I think it was just a misunderstanding.
Kind of.
Reynolds number.
Yeah.
Yeah.
So once you make the air move very, very fast, you increase H, and then you get more.
Yeah.
Actually extract it from the system more. That's a good one anyways. Okay, you didn't talk about radiation, alright? That's fine. So you can go to your seat.
I don't know.
Sit down.
I don't know a whole lot about that.